I hope. Restful, I hope. Let's take no list of things to assign. As usual in my line of work, I got plenty of emails over the weekend, many of which from concerned students asking me things about homework, which is good. It's what you're supposed to be doing. A common question I received was about homework problem number 5 and homework number 6. Sorry, homework 1, question 5, and question 6. Homework 5, question 1, question 6. Now, number 6 specifically is a projectile motion, sort of 2D motion falling example, which is what we're going to be covering today. It's the last part of chapter 1. We're going to close out chapter 1 today, working that kind of an example. But I don't want to just give you this information and send you out and finish the homework without giving you a chance to come back and ask more questions. So, with that in mind, my thought is I'm going to move today's homework and quiz to Thursday so that you'll be able to come in and ask final questions during class on that day. And that way you're not being given any information the day the homework assignment is due. So that's about homework problem number 6. Number 6 is a 2D projectile motion question. The question specifically mentions a bullet fired out of a vintage musket, and the bullets technically are falling after they've been fired. Why is a bullet falling?
It's got drag and air resistance and all that acting on it.
Gravity.
Yeah.
It is currently being affected mainly by gravity. There is air resistance on most things, yes, but we're ignoring air resistance for this class because it's a pain to calculate. So ignoring air resistance, gravity is the only force affecting a bullet as it flies. Therefore, as it flies, it's going to slowly begin dropping downwards. Any object, as long as the only force acting on it is gravity, and if we ignore air resistance, is in a state of free fall. That includes anything thrown, anything shot out of a cannon, but not rockets. Those have propulsion systems. So we're going to do an example like number 6 today. Number 5, because I had a few questions about 5, it is admittedly a kind of a tricky falling question. So if you need help with 5, I really want to get through the projectile motion stuff today. If we have time at the end, we might talk a little bit about 5, or if you as an individual have a question about 5, please let me know after class. But just the announcement is homework and quiz will be moved to Thursday. Additionally, we do have lab this week. I'm still tweaking the lab setup. We might not actually fire the cannons in this room because there's really nowhere for them to shoot. So the setup is still being tweaked, but we do have lab this week, so do come to your assigned lab day. If you cannot make your assigned lab day, let me know. We will work out an alternative. But we will be using, it's going to be sort of a multi-parter so that everyone can be working on a different part based on the availability of the cannon. Do come to lab, and as a general policy, closed-toed shoes are a good idea because today we are beginning the process of doing labs where things are moving, therefore things could fall, and I don't want them to land on your feet. So, general rule for all labs, closed-toed shoes. Which is something you guys are going to have to hold me to because when it's warm outside, I do tend to wear flip-flops. So, let's monitor each other and keep each other's feet safe. Any questions about any of this so far before we continue today? Okay. Hope you all had good weekends. Again, because I didn't see you yesterday, today feels like Monday. I'm going to probably say that every single Tuesday of the entire semester. Please stop me. let's wrap up chapter 1. We left off broaching the subject of the fact that if you throw an object horizontally, its horizontal velocity is not going to affect its vertical falling. This is our beginning process of looking at two-dimensional motion. Motion in two axes at once. So when I throw something sideways, it begins falling. It's going to fall vertically in the y-axis because gravity is going to pull it down, but I threw it in the x-axis. So it still has some motion carrying it horizontally. If I throw it horizontally, it keeps moving horizontally. And so, if we are looking at a question or a system that involves motion in two dimensions, we have to examine each axis separately from one another. If a variable is specifically dedicated to just one axis, x or y, it has to stay in that axis, and you cannot put that variable directly into an equation for the other axis. So, as a quick sort of sample exercise, let's say I throw this marker at 3 meters per second sideways. So its initial velocity, if I'm only throwing it sideways, its initial velocity has two dimensions to it. Velocity initial in the x-axis, if I threw it at 3 meters per second, is 3. But if I throw it sideways and only sideways, what is its initial y velocity?
0.
Negative 9.8 is its acceleration, not its velocity. The moment I let go of it, the moment it leaves my hand and I've thrown it sideways, in that split second, it has not accelerated down yet. Meaning its initial y velocity, if I throw it only sideways, is 0. This is two-dimensional motion. It can be moving sideways, it can be moving in the x-axis while having no initial vertical movement in the y-axis. We're examining its movement in two different ways at once. Sideways, it is moving. Vertically, if you're only looking at how high it is, it hasn't really moved yet. Now, vertically, what's going to happen to it after I let go of it?
And accelerate.
It's going to begin accelerating because of gravity. So, these are the velocities in the x and y axis. We're now going to look at the accelerations in the x and y axis. In the y axis, gravity is going to pull it down. So it's going to accelerate downwards at negative 9.8 meters per second squared. Does gravity exist in the horizontal axis? Is there anything pulling this marker horizontally? Is there anything that's trying to pull it harder in the direction I threw it?
No.
Okay. Gravity on Earth is only ever going to point towards Earth's center. It's only ever going to pull down. Once this marker leaves my hand, there's no longer anything projecting it forwards. It will keep moving at the same velocity as long as there is no acceleration involved. Because gravity is only vertical, its x acceleration is 0. Its x velocity isn't changing. This is also kind of your introduction to one of Newton's 3 laws of motion. You've been working with these your whole life. I can actually go ahead and put this first law of motion up on the board. Just so you can go ahead and take a gander at it. care about the first one right now, so don't let the rest of them confuse you, but we go ahead and put Newton's first law of motion up here because it is relevant to what we're doing right now. Newton's 3 laws of motion are very important for how we understand most things that happen on planet Earth. And the first of Newton's 3 laws of motion says, an object at rest stays at rest, or an object in constant motion, which means constant velocity, remains in constant velocity unless acted upon by an outside force. If I throw this marker sideways, if we ignore air resistance, and we're going to for the duration of this class, if I throw this marker sideways, there's no force acting on it in the horizontal axis. Gravity only points down. That means, as long as there's no force and there's no acceleration in the x-axis, the marker will keep flying horizontally at this speed the entire time it is falling. Acceleration of 0 means this horizontal velocity will be constant. Until something comes in and stops it, this marker will keep moving sideways. The only reason it stops moving sideways is because vertically it eventually has to hit the floor. Yes?
What's the point in ignoring air resistance, like if it affects everything, like day to day?
Most of our examples for this class are going to be designed such that air resistance would be so small or so minimal that it wouldn't matter anyway. Like if we did bother to factor in air resistance as I threw a marker, it might create an acceleration of 0.01 meter per second squared, because this marker with its surface area moving as fast as I can throw it that's not going to create enough air resistance to really matter. And in that situation, it becomes more of a pain to calculate it because it's just not worth it. It's not going to affect it to any significant degree. If we were looking at something flying, that would matter, because the whole point of a jet plane is it's moving very fast and has a lot of surface area to create lift from air resistance. So that would, if we were doing that sort of a calculation, we couldn't ignore it. But I'm going to mostly be giving you examples where we can ignore it because it's just not worth it to try to figure it out at the moment. Because it involves a lot of things like wind speed and the surface area of the object. And then you have to figure out how to find the surface area of a jet, which we don't have a formula for that. In previous classes, when I did have to calculate air resistance, I would have to assume that all of the objects flying were spheres, because we have a formula to find the surface area of a sphere. We don't have the formula to find the surface area of a cow. And for some reason, my previous professors, the object that was always being launched out of a catapult was a cow. There's no formula for surface area cow. But we're not going to bother with that because we're not going to use air resistance yet. So, Newton's first law, I bring it up only to say that since there is no horizontal acceleration, there's no force driving the marker to move in the horizontal axis, it's going to remain at the same velocity. It's not going to change until something else stops it. And if I throw this marker sideways, what's going to be the thing that eventually stops it? Hitting the ground. So, there is no gravity, there is no acceleration in the horizontal axis. That means this initial x velocity is going to remain constant for the entirety of these projectile motion questions. I should go ahead and define that actually. Projectile motion intuitively enough, projectile motion, we are examining the motion of a projectile, but I'm going to actually define the word projectile so that that actually is helpful. A projectile is defined as an object in free fall. remember from last time, an object that is in the state of free fall is only being acted on by the force of gravity. No other significant forces are causing it to accelerate. As long as an object is in a state of free fall, as long as only gravity is affecting it, it is technically a projectile, even if I just drop this projectile. That also means rockets are not projectiles because they have jets, they are accelerating. But drop markers, tennis balls, arrows, all technically projectiles by this definition. And therefore, all of these types of questions that we're going to do, where we're looking at the 2D motion of a falling object, are going to be called projectile motion questions. So, we've been looking at and listing the variables of me throwing a marker horizontally sideways. We've determined it has an initial x velocity and no initial y velocity. It has no x acceleration, but it does have a y acceleration. Now, we've listed everything as an x and a y separately. We've done this because the x's and the y's cannot mix, which means we would have to do our formulas twice. We have to do it once for our x components and once for our y components. This is because the two axes are separate. What happens in one does not directly affect the other. So when we're doing a projectile motion question, we're looking at both axes at once. You have to do it once with the x components and once with the y components. Notice, however, there's one variable between the two that is the same, that I did put an x or a y next to. Which one is that? Time. Time is the same between both axes because time is a scalar. Time doesn't have a direction. If I throw this marker sideways, it has as much time to move sideways as it has time to fall. It's the same time in both axes, so there's no differentiating between the two. It's just the same time variable. It's not a vector. We don't have to bother distinguishing x time versus y time. It's the same amount of time in both axes. Okay? Because time is a scalar, we don't have to differentiate it x from y. It's the same in both, which is very useful because it means we can use one to solve for time. We can plug that time in to the other one to solve for range, which is another word I will go ahead and define for you guys. Range For the sake of this class, the word range is going to refer to the max horizontal distance that a projectile travels. If I throw a marker, and we consider this point in space to be our starting point, and I launch it like this, its range is going to be the distance, horizontal distance, from my foot to where the marker landed. That's just the horizontal distance it traveled. So when a question asks you for range or says the range is, it is referring to the horizontal distance the object traveled. Okay. Any questions so far? what we have here is a different picture of a flying object. Up to this point, I've mostly just been throwing things sideways, but you can throw up and at an angle, and this path right here, this shape, is sort of similar to the problem we did the other day, the jumping basketball player. You have someone who jumps, and some of that is going to include the initial vertical component. You rise, you come to your peak, and then you eventually fall back down. Now, as long as you are a projectile, you are accelerating down. So, in the case of jumping upwards, you have an upwards initial vertical velocity, but notice that this arrow, because we can draw all vectors with an arrow, is shrinking the entire time you rise. That's because the entire time you are accelerating downwards, and your vertical velocity is just going to get smaller and smaller until it eventually becomes zero. So at this point, you're not moving up or down. If you freeze time here, you're only moving sideways. Notice the horizontal component of this motion remains the same the entire time. This person, is this person jumping? No, this is probably something thrown or fired out of a cannon. This horizontal component is going to remain the same the entire time for the reasons we already listed. It's in free fall, there is nothing causing it to accelerate in the horizontal axis, gravity only is vertical, so its horizontal component remains the same the entire time. Only its vertical velocity is going to change. And that is actually what creates this shape is called a parabola. And because it is only accelerating vertically while it moves constantly forwards, that's what creates this shape. It's what creates the arc of an object that, like a person when they jump, or an object when it's thrown or fired upwards. All parabolas are formed from this principle. Now looking at this motion, this distance downfield would be the range. This is the horizontal distance traveled as you leap up. So you're jumping up and forwards. Vertically, you're going to come up and come back down. Horizontally, you're going to come forwards by some amount. The horizontal distance between where you start and where you end is your range. So this particular, cannonball has a range of 60 meters. It was fired and landed 60 feet downrange. Okay. So, we've already listed our variables over there for, say, a sample projectile motion question. If I was to just throw something sideways, we've already listed most of our starting variables. Knowing these things, these would be the formulas that we would use to analyze each of the motion. Vertically speaking, there is a vertical acceleration that isn't zero. So if we were looking at the motion as an object falls over time, because you are accelerating, you want to use equation 3. Equation 3 has an acceleration term in it. This will tell you, as a function of time, where the object is going to be, or vice versa, how long it takes to fall a certain distance. So, for the vertical axis, you have to use equation 3 in most of our projectile motion questions. Horizontally, however, there is no acceleration. There's no horizontal acceleration in this question. That means we could use formula 3 or look at the horizontal axis, but since this term is 0, it just goes away. Horizontally, you're going to move at the same constant velocity. And if this part goes away, what we're left with is basically formula 1. So, horizontally, you can use either formula 1 or formula 3 to look at the horizontal motion of a projectile. So, for the upcoming problems we're going to do, these will be the formulas and Formula 1 that we are going to be utilizing. We're going to work an actual example, and it'll be pretty similar to your homework example in terms of how we work it. We're going to do that in a minute, but I've been talking for a decent amount of time, so if anyone needs a quick break for water or to go to the bathroom, let's go ahead and do that now while I go ahead and check my notes and my emails, make sure everything's good for my example. Considered, and things continue to go positively for you. So, this is going to be our first full projectile motion question. The way that we work this is going to be very similar to the way one would work homework question 6, and also something that we're going to be doing with the marble cannons in lab today. So, a lot of the problems, projectile problems, are going to look very similar to this, so do take notes. So, as I've been doing up here the past couple of lectures, you're going to take something and throw it horizontally sideways and then watch it fall. So, we are standing at the top of a 9-meter tall cliff, which is very tall, and we are going to throw a ball horizontally away from the edge of the cliff at 21 meters per second. Drawing a picture is very useful, so I'm drawing it with you guys. Now, as soon as the ball is thrown, what's going to happen to it? How would we describe its motion?
Start going down.
Okay, it's going to go down, but what is it also going to do?
Go out.
All right, it's going to go out and down at the same time. So its resulting motion is going to look something a little like this. It's eventually going to hit the ground some distance away from the base of the cliff. This is kind of just half of that parabola shape that I showed you a second ago. So we're moving forwards constantly as our vertical velocity begins increasing downwards. It'll move constantly sideways as it accelerates down. So let's start listing what we do know and what we want to know. We're told our initial location in the y-axis is at the top of a 9-meter tall cliff. I'm going to go ahead and say additionally, if this was, say, a coordinate system, if we were making like an XY graph, and this was our vertical axis and this was our horizontal axis, the origin is always 0, 0. This point up here would be 0, 9. We're 9 units up on the y-axis, but we are still in the 0 plane on the x-axis. So another piece of information we can go ahead and pull from this. This is me telling you you can use this as a freebie in these questions. Our original x location is 0. We're 9 meters above the origin, but we are 0 meters horizontally from the origin. Even though we're above it, we're still at x0. Now we are told our vertical x velocity is initially 21 meters per second. If we are throwing only horizontally, what is our initial y velocity? 0. Very good. We only threw sideways. We did not put any power into throwing down. So our initial y velocity is 0. And because we know the ball is going to begin falling, we know its vertical velocity is going to be that of gravity, vertical acceleration. Its vertical acceleration will be due to gravity. But what, if anything, can we say about its horizontal acceleration? It's 0. There is no horizontal acceleration. Gravity is only going to cause it to accelerate down. So we know our starting point, our initial velocity, and our acceleration in both axes, which is very good. Now, the first thing we are asked for, first piece of information we want for the problem is time. How much time is this ball going to spend in the air before it hits the ground? Now, we have a decent amount of information here. We have information in 2 separate axes. So if we start working with a specific formula, we can only put variables into that formula for one axis at a time. My question to you guys, which axis would be the best one to examine to figure out how long the ball will be in the air? Is the x-axis the ultimate determining factor of how long something has to fall?
So it would be
Y.
It's the y. So say I throw 2 different markers sideways at 21 meters per second. I'm going to throw them both at 21 meters per second, but I'm going to hold this one here and this one here. Which one will be in the air longer? Right. If you start from higher up, you have more distance to fall. That means more time in the air. As long as your starting velocities are both 0, your starting height is going to determine your hang time. And that's what we're finding here, the hang time, the amount of time that the ball was in the air. So, as a general rule, the vertical axis will determine time in the air. So, to determine this time, we will examine our vertical variables. So, what formula should we start with? Third formula, very good. So, we're going to start with our vertical ones. So, I'm going to go ahead and plug in y's. 1/2 a squared. So, start plugging variables in so that we can solve for time. What is going to be our total change in location as this process goes on?
Negative.
Right, we're going to fall from a height of 9 down to 0.
So it's going to be negative 9 or 9?
It is negative 9. Delta is always final minus initial. We're going to end at the ground, and we started 9 meters above that. So we displaced 9 meters down, negative 9.
So we've been at the ground, if it was starting from the ground, it would be positive 9, right?
Are you saying if we started from the ground and then threw into a hole?
Through up.
Okay. If we started at the ground and threw upwards, then yes. If we just threw it up to some target 9 meters up, then yes. But eventually it would come back down to 0. The important thing is always, 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 delta anything is final minus initial. Now, what the final versus initial is depends on how you set up your system, but the way that I've drawn this, we begin 9 meters above the ground is 0, so technically the ball fell downwards, a total displacement of 9. And we'll find in a moment that that negative will cancel with a negative over here and everything will work out mathematically. So, our total displacement vertically is negative 9. Our initial y velocity is 0. We only threw horizontally. It's going to be 0 times time plus 1/2 times our acceleration. The y-axis, that's gravity. Then t squared. So, the only variable left is time, so we can now begin to use algebra to get to t equals. We could use a quadratic here, but we don't need to, because this t is being multiplied by 0. So, if I could simplify this down to the next line, this is 0 minus 9 is just going to give us negative 9. 0 times t is 0, so this whole term is just going to go away. 1/2 times negative 9.8 is going to be negative 4.9. So that just gives us a constant equals constant times t squared. Now this is a lot simpler to solve for t than this is. So, get your calculators, break them out, make sure you're able to correctly get to the answer. Both sides have a negative on it, that's just going to cancel, so that'll give us a normal positive amount of time, which is what we should expect and what we would want. So, t squared will equal 9 over 4.9. What does that mean for t.
T equal -8. I mean, -1.8.
Negative?
Oh, yeah, I feel
Yeah,
like
that's
great.
I don't have it written in my notes, so I'm just gonna double check with me on that, but very good. So I've got 1.36. If you round it up to 1.4, that would be fine, divide it by t. What's the units of time we would be using here? Very good. We were plugging in meters per second squared for our acceleration. So that would give us just second on our time. So, throwing from the top of this cliff, the ball would be in the air for 1.36 seconds. Which, again, doesn't feel like a lot, but that's a long time to just be falling. You'll accelerate to a pretty decent speed if you are falling straight, unaided, for over a second. Now, quick concept question before we move on to the next parts. If at the same time as throwing this ball, another ball was just dropped straight down, how long would it spend in the air?
1.36 seconds.
Say it again.
1.36 seconds.
1.36 seconds. As long as the object's initial vertical velocity is 0, and as long as it is only falling, if it is in a state of free fall and it begins at an initial vertical velocity of 0, all objects drop from that cliff, from this height, regardless of mass and ignoring air resistance, are going to spend this much time in the air. This is just the time it takes for something to fall in a state of free fall from 9 meters. Every object will do this, except maybe a parachute. So sort of universally, we can use this method to just find the time in the air something will fall from a height. If you know the height that something starts from, and as long as its initial vertical velocity is 0 and the problem takes place on Earth, where this is gravity, this method can just tell you time in the air. Cool? Yes?
So from 0 to -9, for delta VY, would that change if you use the other formula? So if you did delta VX, would you put the 9 in front? Or does that not change? The method of finding delta V, like whatever you're subtracting from, ever change?
Final minus initial is always true. It's just for our vertical axis, our final point is the ground, 0, at a height of 0, and our initial point was +9. So, delta anything will always be final minus initial. But you're right. In a second, when we look at the x-axis, horizontally we start at 0 and we're going to end somewhere else. So, it's always final minus initial, but what's final and what's initial is going to depend on the problem and your frame of reference. Very, very astute. Okay, so we know time in the air, and this method can be used to find time in the air for anything that is dropped from a standing initial velocity of 0. And again, make sure this is in your notes. The next thing we're asked for is how far away from the base of the cliff will the ball hit the ground? So we are being asked for the range, which is, in this case, going to be delta x. How far did we travel in the x-axis as we were in projectile motion? Okay. I'm tempted to just say as we flew, but technically flying involves force. Now, has everyone copied this part down? Okay. Any objections if I erase this and we start doing the same formula in the x-axis? Okay. talked about range in the x-axis, which means we could change from y variables to x variables. So we want change in displacement in the x-axis, the initial time, the acceleration times time. So horizontally, we want to know range, which means delta dx is actually the thing we're looking for. We are trying to solve for delta dx. That is the thing that we want. We want to know displacement in the x-axis. That's our entire goal here. Now, delta dx equals initial x velocity times time. Our initial x velocity was 21 meters per second, so we'll plug in our 21. Then, plus 1/2 times our acceleration in the x-axis times time squared. What is our acceleration in the x-axis?
0.
0. So plug in 0. This whole thing's just going to go away. It's going to make everything a lot easier. That just leaves us with delta dx equals 21 times time. And conveniently, we already solved for time. So regardless of axis, because time is a scalar, the time spent falling vertically is the same time you have to move horizontally. So this is the time we're going to plug in right here. That's going to give us delta dx equals 21 times 1.36. And
28.86.
very good, thank you very much. Point what again?
56.
Thank you very much. What would our units be?
Meters.
Just meters, actually. We're solving for distance. This is the distance traveled. It's about 29 meters, which is about a football field, about 100 feet. No, wait, football field is 100 yards. A third of a football field. And that is projectile motion. It's the same formulas we've been using, but you're doing it in two separate axes. The two axes themselves are mostly completely separate from one another. The only variable that they share is time. Because time is a scalar, direction does not exist for time, you can put time in both. As a general rule, the vertical axis determines your hang time. So always look at vertical axis for time in the air. Once you know time in the air, that time will tell you how far you were able to fly horizontally. So, nearing the end of the lecture, I am still going to move the homework and quiz to Thursday. Am I seeing it, Joe? Whoops. Still getting used to the technology required for our new setup. Sorry for the difficulties. Homework quiz is still going to be Tuesday, so you can take this information, work on the homework tonight and Wednesday, come with questions on Thursday, or email them to me so we can have them. The one question works very, very similarly. Yes. Gravity is an acceleration. So G is always 9.8, A, and we plug that in for A is the acceleration of gravity. We do have lab this week. If you're not able to make it in person for any reason, please let me know. And let me know when you have questions, and have a wonderful day.